Hey everyone, thanks for joining us. I'm Nancy Atkinson, Senior Editor of Universe Today, and thanks for joining us for our second live interview via Google Plus Hangout on Air. Joining me today, as always, is Fraser Kane, who's manning the control booth, making sure this all works right. And our very special guest today is astronomer Mike Brown from Caltech. Hey Mike, thanks very much for joining us.
You're welcome. This is fun.
Yeah, it is fun.
Possibly.
We'll see. Well, for anyone out there who might not know Mike, he's a professor of planetary astronomy at the California Institute of Technology, otherwise known as Caltech. He specializes in looking at interesting moons and planetary bodies in our solar system, not the least of which he's studying those very distant but very interesting objects at the edge of the solar system. He may be best known for his discovery of Eris, the largest object that's been found in the solar system for the past 150 years. And, of course, that discovery prompted just a little tiny debate about Pluto's planethood status. And he's also the author of his book, How I Killed Pluto and Why It Had It Coming. And unfortunately, I moved in the past 9 months, and my book is packed away, so I can't hold it up as a prop.
I'm a bad self-promoter. I don't even have one in my office to hold up. It looks sort of like this. I don't have one.
I can make it happen. Just you keep talking. I'll make an image appear at some point.
Okay, great. Well, Mike, the latest that I've kind of heard on Eris and Pluto was that, originally Eris was thought to be bigger than Pluto, but now some of the latest research is showing that the two are virtually twins as far as size goes. What's your take on this, and could you explain why there's been different measurements of both Eris and Pluto over the years as far as size?
So, it's actually really interesting. When I talk about, I give talks around the country about all these objects that have been discovered in the outer solar system, and in my standard talk, I'll pick a few of the interesting objects that I discovered and talk about, and I almost never talked about Eris because I have to admit, Eris has been the story of Eris, other than the fact that it's maybe a little bigger than Pluto, blah, blah, blah. The scientific story has been a little bit boring. It's just that it's sort of an object that on the surface it looks like Pluto. It has the same sort of covering of methane and nitrogen ices that Pluto does, and it's a little bigger than Pluto. And that was kind of the entire story, so there really wasn't much to talk about, unlike some of these other incredibly interesting objects like Haumea and Makemake. But the recent measurement, the precise measurement of the size of Eris has suddenly made it much more interesting, because the fact that they're the same size, virtually the same size, within something like 5 miles in diameter being the same size, which is ridiculous. That the two largest things that we know about there are so close to being the same size is just totally unexpected. But one thing we know very well is that Eris is 26% more massive than Pluto, which is actually a pretty big amount. The total extra mass that Eris has compared to Pluto is more than the mass of the entire asteroid belt. This is not an insignificant amount of extra mass in there. So it means that there's sort of an asteroid belt's worth of rock inside of Eris that Pluto doesn't have. So rather than the fact that they're the same size makes people say, oh, they're kind of like twins, the fact that they're the same size, I think, makes them nothing alike at all. Eris is mostly rock with a thin layer of ice on the outside. Pluto is much more ice on the outside and rock on the inside. It's really quite a strange thing. If you had asked me even just 2 or 3 years ago what all of these big objects were going to be like, I would have said, we know about Pluto. We know that Pluto is about 2/3 rock and 1/3 ice, and we would guess that everything else out there in the outer solar system is the same way. And what we're finding is that there's an incredible amount of variation. There are these things like Eris and also the very strange Haumea, which is mostly rock, and Quarwar, mostly rock. There are these other things that are mostly ice, and trying to sort out how all this happened has been a fun but difficult thing to do these days.
Yeah. Could you talk a little bit about the complexities of observing objects that are so far away? I mean, you're talking about what the surface compositions are, and how do we figure that out? I mean, what are the most important tools that you have for looking so far away?
Yeah, so it's of the objects in the outer solar system there, only Pluto and Eris and Quarwar are big enough that you can barely tell. If you take something like the Hubble Space Telescope, you can barely tell that there's a little disk there instead of just a little point of light. So you basically get no information by looking at the object and seeing its shape or things on it. You just can't do it. We can't get closer enough to do it. So almost everything we've learned comes from just a small number of techniques. One of these is spectroscopy. You look at the sunlight after it reflects off the surface of the object, and everything in the universe, every mineral, every ice has a unique fingerprint of the way that the sunlight reflects off of it. The sunlight, some of the sunlight is absorbed, some of it is reflected, and by looking at that combination of who gets reflected and who gets absorbed, and by who I mean the wavelengths of the sunlight, you can tell what's on the surface. So when I say that Eris has a surface that's composed of methane ice like Pluto, that means when we look at Eris and we look at that reflected sunlight, we see the spectral signature of methane, just like is done on Pluto. So spectroscopy has been an incredibly important technique, but these objects are very faint. So the spectroscopy that's been done has mostly been done either with the biggest telescopes in the world, either with the Keck telescope in Hawaii or the VLT down in Chile have been the two biggest contributors to trying to understand the surfaces that way. So spectroscopy is one really important technique for that. The other thing that you need to know, though, to talk about all these things like the densities and the amount of rock and water in them, you need to know the mass. And there's only one way to measure the mass of these objects, and that's if they have a moon. So once it has a moon, you find the moon and you watch how long it takes to go around the object and how far away it is, and you can calculate very precisely what the mass of that object is on the inside. So for Eris has a moon, Dysnomia, Pluto has 3 moons, 4 moons, 5. I lose track. They keep finding them all the time. So having all these moons, you can measure the masses of these objects. But you still need one more thing. Knowing the mass isn't good enough to tell you about the interior. You need to know the size of the object pretty precisely too. And this gets to the original part of the question: is how do you measure the sizes and why have they been changing? The original measurement of the size of Eris was one that we did using the Hubble Space Telescope. And so what we did is we simply looked at Eris with the Hubble Space Telescope as Eris was going by a fairly bright star. And so then we used that star, very carefully and meticulously measured exactly how much the Hubble Space Telescope distorted the image of that star, and therefore how much the Hubble Space Telescope was distorting the image of Eris. And doing that, we could just barely measure the size of Eris. And we said that it was 2,400 kilometers across with an uncertainty of about 100 kilometers. And that was the best measurement that had been around for a while. Just recently, well, a year ago now, Eris passed in front of a fairly bright star. So if Eris is going in front of a star like this, when Eris gets in front of it, the star blinks out, comes back, the star reappears. You can time how long that takes and get a measurement of the size. And if there are 2 places watching, then you get 2 different chords across you, and it's a circle. You can get a very precise size measurement. So the size that was just measured is 2,330 kilometers with an uncertainty. I think the uncertainty is about 10 kilometers. So it's easily within the uncertainty that we had before. Before we said 2,400 with an uncertainty of 100. So 2,330 plus or minus 10 is about what we would expect. But I have to admit, I would have guessed when they made this measurement that it was going to be on the other side. I guessed that Eris was about 2,500 kilometers. And the reason that I thought that was true is because that would make it about the same composition as Pluto. And that seemed the most likely guess. I would never have guessed that Eris was smaller and rockier, and so put those sizes together. So this is where the big surprises come in. It's not that the earlier size measurements were wrong in any particular way. It's just that there was enough wiggle room that a reasonable guess was that it was actually even bigger than that 2,400 kilometers. And I think that's it. I think the spectroscopy, the masses from the moons, and trying to get sizes in a couple different ways have really been the ways that you start to learn about these little points of light. But we can get an incredible amount of information just from those little points of light.
Yeah. How many of those little points of light have you found? How many KBOs have you found?
Oh, I don't even keep track. Hundreds.
Wow.
So there, the big ones. I mean, the ones that are really kind of like, you know, my little adopted children or discovered children are the ones that I really think of and that I'm happiest to have found, because they're the ones that we spend the most time studying. They're the brightest ones we can really learn. So I have sort of my list of 7 favorite big ones that we really spend all of our time doing, and those are the ones that I think have been the most fun to find.
Okay. And how many of those are officially dwarf planets?
You know, dwarf planet is a funny thing. So there is this official list of dwarf planets, which is only 5 objects long, which is a kind of strange thing, because there's a definition of dwarf planet. Dwarf planets are things that are round in the solar system but are not big enough to clear out their orbits. And by that definition, which I think is a perfectly reasonable definition, by that definition there are hundreds of dwarf planets. But the International Astronomical Union, for reasons that baffle me, has decided that they are going to both define dwarf planet and keep a list to say what is and isn't, but then they don't ever update the list or even try hard to figure out what's round and not. So the official dwarf planets, I'm not even sure anymore. It's Ceres and Eris, Pluto, Haumea, Maki, that might be it. But there are clearly many other objects that are round out there, so I sort of don't pay attention to that official list much.
Okay, all right. You mentioned, or you kind of called them your adopted children. Do you have a favorite of your children there?
I can't tell you because the other ones might be listening.
Oh, okay.
You know, each one of those big ones has a little story to tell of its own very own. And when I'm telling that story, I think to myself, oh yeah, this really is my favorite one. So each one of them has something that's my favorite about it. There's Sedna, which is this unique object that's well beyond the Kuiper belt, that actually tells an entire story about the birth of the solar system. There's the crazy Haumea, which is that elongated one which rotates every 4 hours. It's the fastest rotating large object in the solar system, and has got blasted apart in shards of it or in orbit around the sun. I mean, that one's pretty cool too. There's you know, Eris. Eris has always been sort of a favorite just because it was so big, but now Eris is suddenly kind of blowing my mind with what's going on in it. So you know, each of them has its own specialness to me.
Okay. Revisiting Pluto, some recent news came out that there might be a subsurface ocean on Pluto, and just wondering what your thoughts were on that possibility, as well as the possibility for other KBOs having that.
Yeah, I actually think that those sorts of calculations showing subsurface oceans on large Kuiper belt objects have really been out for like 5 years. People have been talking about that sort of thing, and it seems pretty likely. If you have a large icy object, rock on the inside, ice on the outside, you get heat from the interior, from the radioactive decay in the interior. Ice is a pretty good insulator, so if it's insulating at the top and heating on the bottom, you might have some melt somewhere in the middle. It's not like, though, say, Europa. Europa, we now know pretty well, does indeed have an icy, have a water ocean underneath it. The unique thing about Europa's watery ocean is that it's close to the surface. On Pluto and on these other large Kuiper belt objects, it's buried hundreds of kilometers down, which means it's really pretty inaccessible in any realistic sense. There might someday be some cracks that go up to the surface, but it's really hard to tell. We actually just put together what I think of as a really interesting analysis of, again, spectroscopy of objects in the Kuiper belt. And we've been looking at not those sort of 8 big ones that I've been talking about, but the next size down, objects that are sort of the size of Charon, Pluto's moon Charon, and down through there, which really haven't gotten very much attention in the past. And one of the things that we find is, in that size range, these things look like they're covered with ancient water flows. Basically, water flowed on their surface and froze, and then presumably it hasn't been active since the very earliest part of the solar system. But it looks like for objects even of that size, that's sort of the 500-kilometer sized objects, that they had liquid water at least at the beginning, and as it froze, it sort of came up through the cracks and flowed out on the surface. So I think that that water in the outer part of the solar system, liquid water, is pretty inevitable.
Okay. And then another bit of research pointed out that Pluto might also be more like a comet than a planet. And, we know how its atmosphere sublimates away and then reappears. And also it's been hinted that it might have a tail. What are your thoughts on that?
I mean, more like a comet than a planet. I'm not even sure what that means, but it's certainly, the atmosphere definitely disappears. I mean, this is one of the really cool things that's happened in the last 5 years is that we used to be able to only answer these questions about Pluto. It was the only object out there large enough that we could really learn details about it. So we would have to say things like, well, Pluto has an atmosphere, but that atmosphere is going to freeze out on the surface or not freeze out on the surface. We don't really know how these escape processes work, or it's going to go away. Now we have so many objects we can look at. We can see Pluto that has a pretty vigorous atmosphere, vigorous not compared to the Earth's atmosphere, but for out that region. We have Eris 3 times further away with probably has an atmosphere much like Pluto's when Eris is close to the sun, but right now it's 90 AU away. It's the most distant object that we've ever seen in orbit around the sun at this moment, and its atmosphere, whatever atmosphere it has when it's closer in, its atmosphere is frozen solid on the surface. So we can start to see those differences between things that are having them now and will eventually freeze out. There's an object in the middle that's just a little bit smaller. Maki is just small enough that its gravity isn't strong enough to hold on to its atmosphere very much. It's held on pretty well for the past 4.5 billion years, but most of that atmosphere has escaped. The nitrogen looks like it's all gone away, which is a major component on Pluto, for example, and it's just barely hanging on to its last big slabs of methane. And then there's an object like Quaoar, which is a little further out, so it's a little colder, and it has just the tiniest wisps of methane left, and they're all going away. So all of these objects are, if you want to say them in that way, are comet-like. They lose their atmospheres and certainly have tails. If you're losing your atmosphere, that material can get ionized and blown away from the sun. So they have characteristics that are similar to some characteristics of comets, but I wouldn't really say they're much like comets in that sense.
Okay. Well, yesterday we had Alan Stern on our weekly space hangout, and we talked about the New Horizons mission, of course. And since you're so interested in the Kuiper Belt, you must obviously be looking forward to this mission getting out there. What are you most looking forward to spacecraft gets out there?
It's I have had the fun and excitement of getting to watch enough spacecraft mission these days that I know what the real answer is. The real answer is always, you should be excited about the things that you haven't even thought about. I can tell you the 10 things that I think will be really interesting to learn. Actually, one of the ones that I don't hear too many people talk about but I'm really curious about is looking at the number of craters on Charon. Craters on Pluto you won't be able to see very well. The surface gets covered by frost and you won't know what's going on. But Charon is sort of it's an ancient surface, and so looking at the number of craters on Charon will tell us about how much material has been out there. I'm really excited to see these water flows on the surface of Charon that I just talked about on these smaller objects too. Charon also has that what it looks like, that hint that water has flown on the surface. So it'd be really interesting to see, is it generally cover it? Does it come out of cracks? Does it sort of come in volcanoes? Those sorts of things are obvious ones, but I know that as it flies by, we'll see these things that just will totally blow our mind. I spent a lot of time studying Titan from telescopes on the ground from Keck Observatory, and we had it back before the Cassini mission was there, and we had these beautiful maps of the surface of Titan, and there were these features on it, and we made up all these stories in our minds of exactly what we were seeing, and it's really funny to go back 10 years later with real pictures of Titan and realized that just the real things going on Titan, we had no idea. Our preconceptions were just thoroughly wrong. And so I'm sure that the same thing will happen on Pluto, and that's what I'm most looking forward to.
Okay. And then after it flies by Pluto, it's going to be going to hopefully visit another Kuiper Belt object. Do you have a hope for a destination of that?
That people are looking hard for an object that it can go to. It's going by Pluto so fast that it can't make a turn. So the object that it's going to study has to be pretty much directly in the same line it's currently going. It has a little bit of leeway, but not very much. And so far, there is no known object in that region where it's going to go. But it's by bad luck, the region where it's heading is currently finding objects in that region is hard because it's in the thick of the Milky Way, where it's very difficult to find Kuiper Belt objects. It'll be a little bit better in a couple more years, and there should be something there for them to find. It'll be interesting to see. I'll be curious how good of an encounter with a Kuiper Belt object it is, because I know that there are going to be problems. A newly discovered object doesn't have a very well-determined orbit, for example, so targeting it and getting the spacecraft close, and I think it may actually be difficult for the spacecraft to use its autonomous navigation to get closer to, just because the objects will be faint. So it'll be a very challenging encounter. But still, I'm equally excited to see, and it'll be a very small object. It'll probably be a 100 or 200 kilometer object, because that's the common objects that are out there. And I think that's actually pretty interesting to go from, see one of the bigger ones that's out there and also see one of the smaller ones that's out there, as opposed to just going to a bunch of big ones too. So I think it'll be, I'll be looking forward to that one and having my fingers crossed that it works out well.
Okay. Well, I know that you don't always quite look quite so far out in the solar system. Sometimes you look a little bit closer. You talked about observing Titan. Could you talk about some of the observations you've done of Titan, and what are some of the latest findings there?
I did Titan mostly 10 years ago because we could do it better from the ground than it could be done. Well, you couldn't do it any other way. There was no spacecraft there. These days, with Cassini in orbit, it's a little bit hard for telescopes on the ground to compete with big spacecraft in orbit around Saturn, although there are still some things that we do from the ground that are hard for them in Cassini. One of the things that we do on Titan still these days is that we basically have a daily weather report on Titan. We have for 20 minutes almost every day. We use the NASA IRTF, the infrared telescope facility, the small telescope on top of Mauna Kea, and it just at 20 minutes every night it goes and looks at Titan and gets a spectrum, more of these just collecting the reflected sunlight. From that reflected sunlight, we can tell whether or not there are any big storms on Titan, because big storms, just like you can imagine, if there were a big storm on the Earth, it would make the Earth bright in certain spots. It does the same thing there on Titan. When there's big storms on Titan, we can then very quickly take our telescopes and go pinpoint where they are using the bigger telescopes too. So we still are doing that sort of monitoring on a day-to-day basis. But most of the really interesting stuff about Titan, I have to admit, as much as it pains me, is being done by Cassini these days. So we have mostly moved to other bodies in the solar system where we don't have to compete with those billion-dollar spacecraft.
Well, I know you were looking at Neptune recently and Triton as well. What's up there?
The Neptune and Triton. We were just you might have seen those pictures. The only reason we actually took those pictures was we were tuning up our system for our real observations for that night, which is some observations that I'm really excited about that we just did, which is looking at the surface of Europa. Europa, I studied Europa 15 years ago, and then when the Kuiper Belt sort of took over my life, and I'm happy to have a chance to go back and re-look at Europa. One of the big questions on Europa that we're trying to answer is if you can picture Europa in your head, you might remember that it's got a kind of reddish side and then a kind of not red, yellowish side. And the reddish side is, it's going around Jupiter, and its one face is always locked to Jupiter as it goes around. And also Jupiter's magnetosphere, its big magnetic field, is spinning faster, and it picks up stuff and slams it into the backside of Europa. So that dark side, that red stuff on Europa, is stuff. Actually, it's actually stuff that came out of volcanoes on Io and gets picked up by Jupiter's magnetic field, slams into the back of Europa. So one side is all that stuff, one side doesn't have all that stuff. There has been a decade-long debate about what that kind of dark red stuff is. Some people think it's actually salts, and that the salts are from the ocean, and the ocean water percolates up and cracks, goes on the surface, and the water evaporates and it leaves salts. Kind of stuff that you would see in dry lakes, like around here in California, Death Valley, those sorts of salts on the surfaces. Some people think, no, it's not salts at all. It really is just this junk coming in from Io, mostly sulfur coming out of those volcanoes on Io. And if you take sulfur and had an icy surface and bombard that icy surface with sulfur, you get sulfuric acid. So some people think it looks like sulfuric acid. Some people think it looks like salts. It's been very difficult to answer that question because the Galileo spacecraft a decade ago had some pretty primitive instrumentation and couldn't really tell. These days, actually, we can do a better job doing, again, spectroscopy. Spectra is really what I sort of spend most of my days doing. Getting those spectra, that reflected sunlight from Europa, we can actually get better spectra than Galileo could. And with big telescopes like the Keck telescope, we can actually map out the surface. Not as well as if we actually were flying right up next to it. So we can't get the spatial scale quite as fine, but we can get some pretty interesting large-scale structure. And I think we are this close to answering that question. Is Europa just kind of a dead ice ball being pummeled by Io volcanoes, and so it has sulfuric acid on it, or is there really these salts coming up from underneath? The question is interesting because, of course, if the salts are coming up from underneath, that means whatever is in that water, you basically have a record of it on the surface. So rather than needing to go drill down to see if there's anything interesting in the water, you can actually just collect samples or look at the samples on the top. If it's just sulfuric acid and no salts at all, that means that ice shell on Europa could be pretty thick. And if it's thick, it's going to be very difficult both to study the water underneath, but it also means that the potential for interesting chemistry, and I'll say interesting chemistry as opposed to, primitive life or something crazy like that, but you can extrapolate any way you want. Interesting chemistry can happen if the surface materials in the ocean can exchange chemically. If it's a thick shell, not much interesting is going to happen. Sort of like these things we talked about for the outer solar system. Those shells are probably so thick that there's not much interesting chemistry happening in those oceans.
Okay. Any other interesting things that you've been observing recently?
I have. I tend to these days have I split my time between the Kuiper belt and some other object about which I'm currently obsessed, and so my current obsession is trying to figure out Europa. So it's that one's been my fun one these days. Okay. And then the other observations that we do on the Kuiper belt is actually just going out there going out again to the Keck telescope in a couple of weeks, which is to look for more of these moons going around the objects in the Kuiper belt. Finding these moons on objects where we didn't know they had moons means that we get to measure the masses of these objects, understand their densities, understand what they're made out of. Now that we know that the Kuiper belt is so diverse in its composition, and it's, some of them's all rock, some of them are all ice, everything in between. Now that we know about that diversity, we have hints of that diversity. We really want to go to try to map it out and understand why some objects are this way, how many are this way. And to do that, the first step, it's a slow process. First step, we have to find moons. Once we find moons, we have to track their orbits. We have to get the sizes. But that very first step is finding moons, and so that's what we're off in about 2 weeks. We'll be up there. So these days, when I go to the Keck telescope, I'm sure some people have noticed this. I try to post as much data real time as possible. So all the images of the Kuiper belt objects, which they're not the most exciting things in the world, they're little point of light, but the excitement is if there's a second little point of light right there. So I've been putting them up there as quickly as I can. Some of it takes longer than others. The Europa observations took a lot of analysis to figure out what was going on and construct stuff. Although just yesterday, I on Twitter, if anybody saw it, I posted our current map of which part of Europa has water and which part doesn't, and that's the sort of things we're working hard on.
Okay. Yeah, I remember last summer when you did a live tweeting event of observations you did of transit of Haumea, I think it was.
Oh yeah, that was fun.
Yeah, yeah. So, and I think that was just, you said that was a little risky because you weren't exactly sure if the transit was going to take place. I know you're active on Twitter, and of course I love your Twitter handle, Pluto Killer. What is it about Twitter that you find appealing, especially in doing a live event like tweeting live and the tweeting that you do?
Well, it's I think that people a lot of people out there like science, but most of the time when they get their science stories, they get the end result, and I think a lot of people are interested and would like to be able to understand more how it actually happens in real time, and what do astronomers really do. So it's Twitter is a pretty limited tool for doing that, but it's one where if I'm at a telescope, I can just sort of describe what's going on, and people can very casually get a little bit of a feel for what it's like to really be at a telescope on one of these things. And I actually really enjoyed the one where we did the transit of Haumea live. So the way it worked for people who weren't watching is that Haumea is that one that rotates really fast. And so what we were doing was watching how bright Haumea was, which it gets brighter and it gets fainter and brighter and fainter every 2 hours. And we were looking for the signature of one of its moons. It has two moons. One of its moons passing in front of it, which would make the whole thing get a little bit fainter. And we thought it was going to happen this night. We were at a telescope in the Canary Islands off the coast of Africa, because that's where you had to be to see that event that night. And we had done a few other observations, so we had written all the software where we could analyze the data in real time. And so as long as you're doing that, I thought, let's just put it out there. So every data point as it came in, there was about a new data point every 5 minutes. We updated the plot, and you could see our excitement when we first saw the event happen. Right when we predicted that it was going to happen, it got fainter just by the right amount. You could see our bafflement as it didn't last very long. It went back. We're actually still analyzing those data, trying to figure out what the heck happened. It didn't turn out exactly like our prediction, which is always more fun. If things turn out like your prediction, that means your prediction was right, but you didn't learn anything new. It didn't turn out like our prediction. We still don't know what the answer is to that one yet, though. But that was a unique set of observations where we really could very easily put it up in real time. So it doesn't always work out so well that way, but I'm trying to. Some people, in particular, people who I work with, sometimes get a little bit nervous about this because people try to be sort of secretive about what they're doing and what their data look like, and they don't want to be scooped. And I understand that more for sort of my students who are in a stage in their career where they're worried about it. But I think it's more important for me, and where I currently am, that the more people who are interested and can see the way these things work, the better it is for all of us.
Okay. Well, can you tell us about a typical night at observing for you? I know your telescope's a little bit bigger than the rest of us, Keck telescope and other things. What's a typical night of observing like for you?
Well, okay, so I'll describe this one that we just did. We just got back from Keck 2 weeks ago, looking at satellites, looking for satellites of Kuiper belt objects. So you fly out to Hawaii. That's step one. Fly to Hawaii. It's a good way to have to start. I have to convince my wife all the time that it's really, we don't get to have any fun. We stay up all night. We don't go to the beach, but we always go to the beach at least once. Fly out to Hawaii, and you are now jet lagged by about 3 hours if you're coming from California. So come 9 o'clock that night, you're struggling to stay awake, and then you're remembering that the next night, you always go night early, the next night you have to stay up all night long. And so you desperately try to stay awake, never do. Wake up the morning of your observations, and it's really a full day job usually to get ready for that night of observation. So usually, let's say by 10 a.m. I'm in the control room. The control room for the Keck telescope is down close to sea level in the town of Waimea on the Kona side of the Big Island. So it's a great way to do observing it. I was worried about it at first when the control room moved down there from the mountain, just because it's hard to imagine not being at the telescope, not going outside and feeling the weather and looking at the sky. But it works pretty well these days, I have to admit. And being at sea level, your brain works a lot better. So it works out that the astronomy works out much better. So by about 10 a.m. We are working on getting our whole observing sequence for the night that we think is going on, contingency plans for what if this doesn't work, what if this doesn't work, what if some clouds come here, what if this. So, for one night of observing, we have these huge lists of all these different things we might do at every moment. By about 2 p.m., the telescope has been, in the daytime, the telescope is worked on, maintained, everything else. By about 2 p.m., they release the telescope to us so we can then start calibrating the instrument that we're using that night, testing it, making sure all the detectors are okay, making sure we have the calibrations that we need, the settings all done. By about 5 p.m., the sun in Hawaii, it's near the equator, so it doesn't go too late or too early. It's always around sort of 6:30-ish p.m. So around 5, we walk off and get dinner for the night, which is one of the nice things about being down at sea level in a town. You just, walk to your favorite restaurant in town, get dinner for the night, go to the grocery store, get snacks for all night long. The best thing about observing in Hawaii and in Waimea is that rather than, when I'm at other telescopes and you get your snacks and they're like chips or some crummy things, in Hawaii I always get this beautiful fresh Hawaiian poke and just eat it all night long, and I love observing and eating poke. I'm now spoiled with the Hawaiian poke observing. So as the sun sets, and as soon as the sun sets, for the first maybe hour, it is the busiest time of the night. So you're talking to the telescope operator is on a video link up on the summit, and the operator opens up the telescope, is checking out the telescope, pointing it in different places, focusing it. You're testing out the instrument, making sure everything's okay, and then when you finally get dark, you start for the night. And so in a night like the one that we were doing, looking for satellites, we would first go. We have our list of where things are. We go to our first Kuiper belt object, and the only way we can see those satellites that are in really close is we have to use adaptive optics. We have to correct for the smearing of the Earth's atmosphere. And the way you do that is by firing this powerful laser up in the sky and watching it be affected by the Earth's atmosphere and correct it in the same way. And so we fire the laser up, but to fire the laser up, you have to get permission from U.S. Space Command so you don't blast out some satellite. And they tell you, for every spot in the sky you want to look at, exactly when you can and cannot shoot your laser. So you're about to go here and you suddenly realize, oh no, Space Command says we can't do that, so you have to go off and do something else. So after this incredibly busy and stressful beginning, it goes through periods of sort of totally boring to totally stressful once again. So the totally boring is when everything's going well and you're going to be watching this one object for an hour or two, collecting data. You're sitting here at this computer screen, you're pressing buttons and collecting data, and there's usually two of you, at least when we do this program, one working on the telescope and one looking at the data as it comes in and analyzing it and trying to see how it's looking and making sure everything's okay. And as long as everything's okay, it's kind of boring. Something always breaks because these are big, complicated machines. And then it gets exciting again. You have to figure out what crashed and why, and but it sort of goes like that all night long. And then a cloud comes in and everybody gets depressed because you're about to get this great data and this cloud just destroyed your data, and you obsessively watch the satellite picture hoping that maybe that cloud's going to be the only one. It goes away, then it goes away, you start again, and finally it's 6 in the morning and you're exhausted, and you go sleep for about 4 hours and start all over again.
Cool. That's great. Fraser, do you want to take a look and see if we have any questions from people?
Yeah. So we've got a bunch of questions piling up now, and so again, if people want to ask some questions for Mike, just on the Google Plus page where we're having the interview, you can just type in a question, and I will pass it along for you. So, a couple of questions I think have already gotten answered. So Ian O'Neill from Discovery Space wants to know, what's your opinion of the likelihood of Pluto playing host to a debris cloud of dust and tiny moonlets? And this is sort of one of the I guess the threats that Alan Stern was talking about the New Horizons. As it passes Pluto, there could be this dust cloud hazard that might wipe out the mission and we'll have to take evasive action.
Yeah, he's looked into that much more than I have, because it's more of an operational question rather than a science question. I mean, there certainly is dust, some amount, and the real question is just how much. So if you have all these moons out there, things will hit them. You'll have these little dust rings, and I don't think nobody really has enough understanding of what's out there to be able to make any sort of reasonable prediction. So, I don't know how you deal with that as a spacecraft operational person like Alan. You have to decide what to do in the face of not knowing the answer. But I haven't thought much about it, because luckily I don't have to fly a spacecraft through the middle of all of it.
Let's see. Oh, and so Don Denisiak says he wonder if you could do an on-air hangout like what we're doing right now, but from the Keck control room, so we can peer over your shoulder.
Yeah, actually, Nancy and I talked about that. I think it would. We could do something. I like the idea. It's a combination, as I said before, of really intense, at which point what you'll see is a bunch of frustrated people running around typing on stuff, and also really boring, where we're like trying to stay awake. But I would like to figure out a way to do something like that. I think it'd be really fun.
Now, I actually had a question. Yeah, we'll figure something out. I had a question actually for you. Based on the observations of the Kuiper belt objects that you found so far, what do you think is sort of the constituency of the outer solar system? Are the objects going to be getting sort of smaller and smaller, or do you think there's some big monsters out there that we just haven't found yet?
So, if anybody's been paying close attention to the discoveries in the outer solar system, there was this flurry of discoveries of big objects. The big objects that I talked about earlier on, like the Eris and Makemake and Sedna and Haumea and Quarwar and all those ones whose names you might recognize, those were all discovered 6, 7, 8 years ago, all at once. And the reason is because that's when the technology got to the point where we could do these big surveys of the whole sky, and we found them all. I mean, those are the big ones, at least the big close ones. Now, no survey is perfect. When we did our big surveys of the outer solar system, we knew that we had some pretty early detectors, because this is one of the ways you sometimes get to do the science first, is you take the earliest versions, even though you know they're not perfect, and you slap them together with bubble gum and baling wire and make it all work. But sometimes your bubble gum gets in the middle of your camera, and so you can't see something. So there will inevitably be, I think, a few objects of the moderate size still to be found, but there are probably not many in the near part of the Kuiper belt. Some of the objects that we found, though, are on these very elongated orbits, and things on elongated orbits spend most of their time at the distant part of their orbit, where they're the faintest. So we may have missed some of those. We certainly have missed some of those. What I think is really the interesting part, though, is the one object we found, Sedna, which is not really part of the Kuiper belt. It's the only object that we've ever found, that anyone's ever found, that's really beyond the Kuiper belt. There are a lot of objects on extended orbits, but they always come back to the Kuiper belt, thus they're part of the Kuiper belt. Sedna has this elongated orbit, but it never even comes to the Kuiper belt. It's totally distinct. And the fact that it's so far away and on such elongated orbit, I mean, it's on a 12,000-year long orbit, and it goes 1,000 AU from the sun. There must be many, many, many objects like that we haven't seen yet. Now, we've estimated that there could be as many as 60 or 70 Sedna-like objects, the size of Sedna. If Sedna is sort of half the size of Pluto, maybe a little bit smaller, if there are 60 or 70 of those objects in that region of space, then the biggest things in that region of space are clearly going to be bigger than Pluto and Eris and Triton. You could imagine, I don't know if it's true or not, but you could easily imagine that there are things that sort of rival planetary sizes. There could be things the size of Mercury, the size of Mars out in that region that are so far away that they're currently too faint for us to find.
And so you would see then a new technological advancement bringing a whole nother range of those objects into play. What would be that technological advancement, do you think?
It's on its way. So there need to be two things that happen. The first one was that we got these big digital cameras. Just like everybody else, our digital cameras now have more megapixels than they used to, and that's an incredibly important thing for astronomers. When we started doing this survey of the outer solar system in 2002, our camera had 180 megapixels, and it was unprecedented. That was back when the one in your pocket had 0.8 megapixels. Now you probably have 180 megapixels in your camera or on your cell phone.
Yeah, on my phone.
But at the time, that was crazy and unprecedented. That technology is just continuing to go, but what needs to happen now is to take those cameras and put them on big telescopes. So we used, to find all these big objects, the bright objects, we used the 48-inch Schmidt telescope, the historic 48-inch Schmidt telescope at Palomar Observatory that was built back at the same time the 200-inch telescope was built at Palomar. And it was built as a wide-field camera using photographic plates to survey the whole sky. We took out those photographic plate handling capabilities, slapped on this new camera, and could cover big areas of the sky. But it's a small telescope. A 48-inch telescope is, by modern standards, pretty tiny. So if you can take, yeah.
Yeah, not a 10-meter telescope.
Not a 10-meter. If you can take one of these big cameras now and put it on a big telescope, you're in business. And this is actually happening. The next, I think the next big thing in finding huge numbers of Kuiper Belt objects and distant faint ones is this project that's underway in Chile right now. It's the LSST, the Large Scale Synoptic Telescope, is a project, a consortium of many universities plus the National Science Foundation to build a 6-ish meter telescope with a huge camera, and it will cover the whole sky multiple times a month and find these sorts of objects. It'll get down to much fainter things than we've seen before, and we will inevitably, we'll find a lot of small ones in the close parts of the Kuiper Belt, which will be very exciting, but we'll start to get to be able to see what those populations even further away are. So I am really excited about this project coming up in sort of the 2020 timescale.
And so that'll be the same thing. There'll be this, once that new system gets operational, then there will be a whole new group of largish objects probably discovered within, a similar time frame.
Yeah, I think it'll actually happen in a year. As soon as that's underway, the whole sky will be covered in a year, and that covers the whole sky, and if it's there, and you find it. So
right.
There'll be just this pulse of not only 10,000 new small objects, but a couple of really big distant ones, which I'm excited to see what those objects look like.
Right. So we'll get simultaneously, we'll get a whole class of sort of scares about asteroids and discoveries of new Kuiper Belt objects all at the same time.
Yeah.
And if anybody wants any more information about finding more Kuiper Belt objects, Emily Lachdwal at the Planetary Society blog wrote a post just this week, Wednesday the 16th, about this, and she's got a really neat infographic there showing the positions of the largest known Kuiper Belt objects.
And before we actually let you go, can you give us a definitive pronunciation of Kuiper?
I can tell you the one that I use, and it's one that I was told by a person of Dutch ancestry is the correct Dutch pronunciation, and that's Kuiper. It said if you can do something slightly different with that vowel, you're better. But Kuiper is closer than Kuiper, so Kuiper is what I say.
Okay.
There we go.
I don't know what Kuiper actually said. That would be the real question, is to ask him. But
well, there's some Kuipers still out there, I think.
So his daughter is still around, so we should find her and ask her.
Okay.
All right. Well, I think we've wrapped up the questions from the audience. I think running at the end of our hour, so why don't we let Mike go and. All
right. Well, thanks a lot, Mike, for joining us today, and we really appreciate you taking the time. And yes, we will take you up on your offer to look over your shoulder while you're observing at Keck.
Or even if you're just like going and getting lunch, that would be great.
Yeah, sure, that's fine too.
What it's like to walk to the supermarket and go to the subway at the Keck telescope. It'll be very exciting.
Yeah.
That'd be fun. I would do that.
Okay, great. Well, thanks very much, and thanks everyone for joining us today.
Thanks a lot.
Thanks, everyone.
Bye.